Hi everyone, welcome to Differential Calculus. Today we explore lesson 4.7, optimization part 1. Optimization is the most important application of derivative. 1. Optimization. In an optimization problem, we optimize the objective function given a constraint equation. The objective function usually have two variables, and we either maximize or minimize it as for the constraint equation. It usually has two variables, and it is useful to reduce the number of variables in the objective function to 1 by substitution. The goal in an optimization problem is to figure out the optimum value of the objective function within certain constraint. Let's take a look at some example. 2 example. Number 1, a local farmer has 400 feet of fencing and wants to enclose the largest rectangular field possible that borders a stray river. That is, the farmer wants to maximize the area given 400 feet of fencing. No fence is needed along the river. What would be the dimensions of such rectangular field? Let's take a look at a few rectangular field. Here come the river. The field can look like this, or it can look like this, or it can look like a square. So which one is it? We don't know. To do the problem, we only need one sketch. So let's take the first one. The width is x and the length is y. Objective function. We want to maximize the area. So that is area is xy. And then the constraint equation 400 equal to x plus y. In the constraint equation, we saw for y. It's easiest to do. Y is equal 400 minus 2x. And we're going to use this. I'm going to sub into the objective function a equal x, y. So now we have a equal to x and y is 400 minus 2x. Ta-da! A is equal to 400x minus 2x squared. Yay! This is the function in terms of x. We can use the derivative to figure out the optimum value. And in this case, the global maximum. This is an upside down parabola. And as you can see, there can only be one local maximum. So that would be based on the theorem that we learned in the previous section, the global maximum. So let's do it. Now, use calculus to find the global maximum. A prime is 400 minus 4x and set equal to 0. So x equal to 100. And that is it. only one critical number. So it has to be the absolute maximum because it is an upside down parabola. If it is not an upside down parabola, we have to do the second derivative test. Once we figure out x, so y is equal to 400 minus 2x. Y is 400 minus 2 times 100, and y is 200. Ta-da! That is it. We got the dimension of the rectangular field. Let's do another one. Exercise number 2. Suppose you are an engineer and your task is to create a box that minimizes the surface area. The cost of material used to make the box. Well, that is what the surface area is known for. Your box wants a square base and open top box having a volume of 500 cubic centimeter. How would you design such box? First thing is sketch out the box there. Square base there. XX. So I mean the height is Y. Yeah, box is open top. Okay. We want to minimize the surface area. That is going to be the objective function. So objective minimize surface area of the box is the base area plus the side area. X squared plus where we have 4 sides, 4x, y. Constraint equation. That would be the volume. 500 equal to x squared y. Here it would be best to solve for y. Y is 500 over x squared. And now we take this sub into s equal x squared plus 4xy. S equal to x squared plus 4x. Y is 500 over x squared. S is x squared plus 2000 over x. Ta-da! Now we're gonna do the S prime 2x minus 2000 over x squared equal to 0. Figure out the critical number. Hopefully there's only one. From here we do a common denominator. So it's 2x to the 3 minus 2000 over x squared equal to 0. Well, the bottom cannot be 0. So 2x to the 3 minus 2000 equal to 0. And from there we see that x to the 3 is 1000. So x has to be 10. Ta-da! We'll have one critical number. And hopefully that is the local minimum. Well, we can test critical number. And it is a pretty simple test here. You either use the first or the second derivative. So critical number is 10, right? Pick a number here. So f prime of 0. Let's say put 0 in here. Then we have, no, we cannot use 0 because that is the dimension of the box. It has to be more than 0. So f prime of 1. And f prime of 1 is less than 0. Now, let's say f prime of 11. Plug it into the derivative function. We see that it's more than 0. Decrease to increase. So f of 0 is local minimum. Ta-da! That is it. Right? One local minimum. That is the absolute minimum. X equal 10. So y is 500 over x squared. We do the sub. And that is 500 over 10 squared. So y is equal to 5. Ta-da! Got the dimension of the open box. Example 3. What is the optimum ratio of height to radius of a cylindrical soda can that minimizes the cost of metal used to manufacture the can? Let's draw the cylindrical can here. We want to minimize the cost of metal used to manufacture the can. That is the surface area. Let's cut the can here. Cut, then we have the top border. It should be the same as the top. And we have the body. That is the radius. Radius. And this is the height, h. So here come the height h. And the body, the length is the circumference. 2 pi r. Okay. The area here is pi r square. So area 2 is also pi r square. The area 3 is 2 pi r h. Objective is to minimize surface area. Surface area is add up all the area. 2 pi r square plus 2 pi r h. Constraint equation is the volume, and that is pi r square h. Here it would be best to solve for h. H is v over pi r square. Right? And we're gonna sub it into the surface area function. 2 pi r square plus 2 pi r h. Surface area becomes 2 pi r square plus 2 pi r h is v over pi r square. Now we have 2 pi r square plus 2 v over r. It's very similar to the problem that we did earlier. Hey, look at this. Similar. So that means when we find the derivative and set it equal to 0, we only get one critical number, and that critical number is is the one that we are looking for. Okay. So let's take a look at the derivative. S prime is 4 pi r minus 2v over r squared set equal to 0. Using common denominator, we have a 4 pi r cubed minus 2v over r squared equal to 0. So here, pi r to the 3 minus 2v equal to 0. R to the 3 is 2v over 4 pi. R is v over 2 pi to the power 1 over 3. Ta-da! Let's take a look at the high edge and see how they relate to each other. Now, h is v over pi r squared. Do the substitution here. V over pi, v over 2 pi to the power 1 over 3, and then we square this. V over pi v 2 over 3 over 2 pi 2 over 3. V over pi times v2 over 3 over 2 over 3 times pi 2 over 3. From here, we can simplify the v and the v2 over 3, which give us v1 over 3. We can also simplify pi and pi 2 over 3, which give us pi 1 over 3. And the 1 over 2 over 3. Okay, so that one is the we can flip it. So that we have v to the power 1 over 3 over pi to the power 1 over 3 times 2 over 3. Oh, look at this thing here. V over pi to the power 1 over 3. And then 2 over 3 can be written as 2 over 2 to the 1 over 3. So what this tells us is we have 2 times v over 2 pi 1 over 3. And it is exactly 2r. Oh my God, look at this thing here. Pretty cool, huh? So does the optimum height to radius ratio for a cylindrical soda can is h over r, 2r over r, and that is 2 over 1 or 2 by 1. Thank you for watching. I hope you found the content useful. Please like, subscribe to help the channel grow. I'll see you in the next video.